All right. Good morning, everyone in the US, and good afternoon, good evening elsewhere across the globe. Welcome back to the fifth and final day of this summer school. We hope you've all had a great time so far and learned a lot from all of the lectures, and especially through your hands-on work with the hackathons. Today is also the concluding day for the hackathon. Many of you have submitted all of your work through the sort of consolidation slides yesterday, and we will be presenting your latest and greatest results today, sort of collated together and compiled. But before we get to that, we do have a very exciting lineup of speakers for today. Today we'll be delving into some very exciting and advanced topics, including unsupervised learning, deep generative models, and so on. To start off the day, it's my great pleasure to invite Mustafa, who is a colleague from Lawrence Berkeley Lab. He's a deep learning expert, and I'm just going to pause for a moment as we sort out a brief technical issue. My apologies. Please bear with us for a moment.
Yeah, it looks like we're not actually streaming at the moment. Brett's restarting the stream. Okay, cool.
So should I start from scratch?
Yeah, I think you should start from scratch because I don't think anything was going out.
Oh, I see. Okay. No worries. And Mustafa, when I mention your name, can you turn on your camera?
Okay, sounds good.
Good morning, Claire.
Hi. Have you guys started?
Sort of. We're running into a streaming issue.
We are live. We are live. So yeah, go ahead, Karthik, anytime.
All right. Thank you, Brett. Well, good morning, everyone, and good afternoon, good evening for folks in other parts of the globe. Welcome back to the fifth and final day of this summer school. I hope you've all enjoyed the talks so far and learned a lot through the hands-on exercises and the hackathons. Today is also the concluding day for the hackathons, and we'll consolidate all of your work and present your results at the end of the day. But before we get to that, we have a very exciting lineup of talks and speakers on topics such as generative modeling, unsupervised learning, physics-informed learning, and so on. First of all, I'd like to invite Dr. Mustafa Mustafa to join us. He's our first speaker for today. Mustafa is a deep learning expert and is actually a colleague of mine at NERSC at Lawrence Berkeley Lab, which is the supercomputing center. He's a close collaborator and a dear friend, and we work together on many projects. Mustafa is a physicist by training, and his current research is on applying deep learning to problems in the physical sciences, including spatiotemporal systems such as turbulent flows and climate dynamics. His expertise is in training and convergence of deep learning models at large scale, neural architecture research and optimization, and deep generative modeling. Today, Mustafa is going to present to us on deep generative models.
Hi, good morning, everyone. Still trying to turn my camera on, but we'll see if Zoom lets me in a little bit. Okay, so good morning, everyone. I think in this, thank you, Karthik, for the introduction, and thanks to everyone to the organizers for inviting me to give this talk. Hi, I think you can see me now. So in this talk, I'll try to give, it's a 1 hour talk, so it's really difficult to cover all the topics that are related to deep generative modeling. So what I'll try to do in this talk is just to overview the lay of the land in a very gentle sort of introduction fashion. But there are a lot of references in the talk where you can just go and delve deep into the particular topics, and there are also some references at the end. This particular topic is very close to what I do, and it's very dear to me because I think there's a lot of hope in using generative models to develop data-driven models of the physical world. And this is the larger picture where generative models contribute to in all physical sciences, not only in climate and Earth systems. And essentially, the basic idea is that you have up until now, all of our models of the world has been kind of like a reductionist approach, right? We understand the physics, we understand what is the underlying principles, and then we build from there, or we simulate them from an ab initio sort of perspective, and then we hope that the emergent properties that we see actually in the macro world will appear, right? And as you know, you're working in climate. For example, and all Earth systems, and especially climate, it's very hard to simulate large-scale systems that way. Can we use data-driven methods to do it? That's the question. And deep generative models is very related to that question. So in this talk, I'll give an introduction to what generative models are, and then I'll focus most of the talk on latent variable models. So it's hard to start any generative models introduction without showing something like this. Which of these faces is fake? You can see like there's a lot of, this is very high definition, a lot of very consistent features, the hair, the entire face, the background, everything there is realistic. The reality is that none of these faces is actually real. All of them were generated using a deep generative model. You can ask the same question about things like this. This is the atmospheric upwind velocity over the Pacific. You can look at them by eye. You can look at all distributions, and you'll see that this is actually, all of these are fake. None of them are produced by a real simulator. And it's not just pretty pictures, right? Like this is one example here. If you look at Rayleigh-Bénard and try to use a deep generative model to generate Rayleigh-Bénard states, it's not just they look pretty and all that is fine, but they also are consistent with the original data. So it's not just pretty pictures. You can use it to do things other than images, like for example, generating music is something that you can do using generative models. Unfortunately, I can't make you listen to some of this, but you can visit the website and see, like it's really impressive how much these models learn about the training data. Okay, other uses that I thought could be relevant to this talk are things like, for example, denoising or image inpainting, right? So like if you have you look at the upper figure or picture, you can see like if you have like part of the image is not there, the generative model can learn how to synthesize texture or resynthesize that or inpaint in a way that is consistent with the rest of the image. And you'll see it will appear in a second. You can use that same principle in things like, for example, people have very recently used it to reconstruct observational gaps in historical temperature measurements. You can see this in the lower plot. You can also use generative models to do domain-to-domain translation. In this case, it's image-to-image translation, but there are all sorts of domain translation problems in sciences, right? So look at the upper left plot. You can see that you can go from, for example, same picture, you can take it between summer and winter. People have recently used the same technique to do projections for or visualizing how climate disasters would look like in the near future. You can use generative models to do things like super resolution. They help significantly with super resolution. The left plot is using, super resolving a lower resolution image using bicubic, and then the one in the middle is using a generative model. And you can see that it's very close to the original. You can also use it to do data imputation. So if you have certain parts of your data distributions are missing for certain instances of the data, you can reconstruct those. So you can look at this, for example, here, like this face, for this particular person, the sad face is missing. The generative models can learn how to reconstruct the sad face, even though that it has never seen a sad face for that person. And this is also important. Data imputation is important in multiple sciences. They also learn they learn very meaningful features about our data. So this whole business is related to representation learning, right? And I'll talk a little bit about this later, but they learned essentially representations that are somewhat disentangled. We can argue how disentangled they are or not, but they are somewhat, for example, if you have smiling pictures of smiling women and then subtract from, yeah, probably it's better to talk about this a little bit later, but essentially these representations are actually, you can do arithmetics on these representations to, that correspond to the semantically meaningful things like, for example, glasses or gender. Okay, so that's an introduction. Now I'm gonna delve into a little bit into the details. Let me first set up where this comes from. So I know that you have a talk on unsupervised learning later today, but it's very important to introduce this at this moment. So first, let's remember what supervised learning is. The setup is that you have some data sets that are sampled from an underlying real world distribution, and then you have some labels for those data sets. The labels could be whatever, right? Like the labels classification or some value for every one of the examples or whatever it is, right? And then what you try to model is the conditional distribution. What is the distribution of labels given a certain example, right? That's what you do in supervised learning, and that's probably, I've seen a lot of that this week. In an unsupervised learning setup, you don't care about the labels, even if you have them. That's not the main issue. What you're trying to do is you're trying to say, like, can I reconstruct? Can I explore the underlying structure of the real data distribution P of X? Can I model that? And of course, if you model that, there are many things that you can learn. You can sample from it, right? You can do data generation, you can do data imputation, you can do all the tasks that we looked at earlier. And most importantly, you can do dimensionality reduction. And dimensionality reduction is also related to the idea of meaningful representations and disentangled representations and all of that. So really the problem of unsupervised learning is, how do you, given a set of data, you assume that those data are IID, right? Like they are sampled uniformly and independently from the real data distribution. How can I build a model that approximates the real world P model? And that's what generative models do. A simple example is just the classic density estimation methods, right? So you have a real data distribution in blue. This is a mixture of two Gaussians, and then you sample the points in red, and then you're trying to approximate that with your model, right? This is the dash black here. So it's just a classic density estimation, but we want to do that in a very high dimensional spaces for real images, for example. So the first thing that you can try to do is you can think of, like, yeah, let me try to do that explicitly, model the true distribution. So what is the true distribution? P of X, which is the probability of an image X, right? And you want to get P of X in your generated model or in your density estimation to be as close as possible to the probability of that image in the real data distribution, in the real world, right? From the true underlying distribution. The way that you do one way to do this is to use essentially an explicitly construct the probability of the image as a decomposition of the probability of every pixel. So essentially, you learn the probability of xi given all the previous pixels. This is just like the classic graphical model representation. And then you try to fit this using maximum likelihood to the real data and maximize that this probability matches the probability that you see in your real data. And there are lots of models like this, PixelCNN, PixelRNN, WaveNet, and a lot of other work on this. And that's not what I'm going to focus on today. But it's there, and this is the most straightforward way. You're just attacking the problem on its head, right? And the problem here is approximating the P data, which is the P real, right? Like the real data distribution using a model distribution. Okay, that said, I'm gonna focus today on a different type of models, which are the latent variable models. Let's see, before we get in, let's try to remember one thing about all of machine learning. There is an underlying assumption in everything that we do in machine learning. And that assumption is that the real data, the real world data lies on a lower dimensional manifold embedded in a larger dimensional space. An example just for visualization here, you have a 3D space and your real data lies on a 2-dimensional manifold inside that 3D space. So the idea here is that if you have an image that is, for example, 1024 by 1024, that's a 1 million dimensional space. Your real data doesn't have, the manifold of your real data doesn't have a million components, right? A million dimensions. It lies on a much, much, much lower dimensional manifold. And this idea is very central to all of machine learning. This is how we say that we can learn meaningful features that will allow us to do downstream tasks like classification, regression, or whatever it is. And otherwise you can't, if all of your space is your hypothesis space is a potential data point, then you can't do any of that, right? And in unsupervised learning, or in this case, generative models, what we try to do is we try to find that manifold. You can say, I want to find it by actually estimating the density. You can say, and directly reconstructing, a density estimator of this. You can say, I don't really want to find an explicit density, but I want to be able to sample from it. You can say, I want to be able to walk on it. All of these things essentially boil down to approximating that real data manifold, lower dimensional real data manifold. So in latent variable models, the way we say, okay, yeah, that's great. So it is on a lower dimensional manifold. How about we try to directly model that? So essentially assume that I have a latent space that is much lower dimensional, and then build a model that will map points in my latent space to the full space of my data. For example, I can have a latent space here that is 10 dimensions, and then real data that is 1 million dimensions, as in the case of an image, right? And to depict this, this is essentially what we're looking for, right? Like this is a very complex, higher dimensional data manifold embedded in 3D space. Can I find a 2-dimensional latent space that will map every point here to a point there? And that is what we're trying to do, and we're trying to do it in the latent variable models. We're trying to do it by constructing a latent space and trying to learn this mapping. Yeah, of course, what would this allow me to allow? So many things, right? This is I know this. This is intractable, right? Like I don't know where the manifold is. You can't know anything about it. Can't sample it. But this is tractable. Depends on what tractable means here. But you can walk on this manifold. You can see the relationship between different points in this manifold. You can do if there is time in one of the dimensions. You can do, for example, forecasting. You can essentially search this space. You can't search this space. Imagine that every one of these is a molecule, for example, a drug molecule in pharmaceuticals. This, you can't search the space, but this is a space that you can search, right? There are lots of things that you can do in this space. Most importantly, from a machine learning perspective, you want to have disentangled representations in this space, which means that the different directions in the latent space would correspond to features that are semantically meaningful, something that you care about, or represent something that we can understand as humans. And it doesn't necessarily, it could be like the actual axes, right, the directions, but it could also be just a direction in that space. Okay, so that's it. Now I'll move on to the actual models. We'll talk first about variational autoencoders. I would assume that you have seen autoencoders before in this, at least in the school. And the main idea of autoencoders, this is not yet the variational autoencoder. It's the classic one. The main idea here is that you have two functions. One of them is an encoder, another one is a decoder. The encoder tries to map the input data point, let's say an image, into a much lower dimensional space. And then the decoder tries to take a point from that space and reconstruct the original image. And the main idea here is that if I have an information bottleneck, if the information, if I can't learn the identity essentially, and just if I can't pass every single pixel from the input to the output, the information has to pass through a lower dimensional representation. And if there is no leakage between them, then the latent representation would be something that it will be a lower dimensional. That's first. Another thing is that it will capture features about my input data that we care about, the most prominent features, right? And the way that you train this, you just use a reconstruction loss. You say like, this is lower dimensional, lower in dimensions than the input, and then I try to make the output look the same as the input. I can do it as an L2, L1, whatever it is, as a reconstruction loss. And I'm sure you have seen this before. Depending on the dimensions of Z, the reconstruction fidelity can change. For example, if Z is very small, then you only capture the main features. If Z is very large, then you allow more information to pass, and then you capture much more about the input X, and then you have a much lower loss and higher fidelity reconstruction. Now that's great. This is a latent space, right? This is a latent space, and this is an output space that is higher dimension. This is lower dimension, but this is not enough for our downstream tasks. So we can say that this is already a generative model, right? But it's not enough, right? Because one thing that you would want to do, you want to be able to sample from your latent space and then decode the points that you have in the latent space into the output space. And if you have no constraints on how the structure of this Z looks like, any point in there could potentially be a meaningful point. And so how are you going to sample from that? So in this discussion, you can think of, I want to impose a prior on the latent space structure, and that prior has to have some sort of So I can just choose whatever I want, and then if I have a prior, I can sample from that prior and then do inference, right? I can calculate P of Z given. This is P of X given Z. Sorry about this typo. This is P of X given Z. But this is what you want to do, right? So you want to get the inference. What is the probability of X given Z? To begin with, this doesn't do any probabilities. This is a static thing, right? For every X here, there's one Z. For every Z, there is one X prime. So we want to add some sort of stochasticity in there. Before I get into this discussion, I want to tell you that everything that I'm going to talk about has actually a very well grounded interpretation in probabilistic. It's a probabilistic interpretation and probabilistic deep learning, right? And the full discussion of how to derive a variational autoencoder and derive its loss and all of that needs some development, which I won't go through here. But essentially, the main idea is that we want to have a maximum likelihood estimation on the real data distribution P of X. We can't do that directly, so what we end up doing is we derive an upper bound or a lower bound in this case on the log likelihood of the real data, and that's just an approximate bound. It is not exact. That is developed in the full VAE paper, and this is an excellent tutorial on the derivation of the full all the equations here. And what I'm going to use now in my arguments, I'm just going to motivate it in a very hacky way, these terms, but it's not the full probabilistic picture. Okay, so we said that we want this autoencoder to be stochastic. So the first thing that we can do is we can replace the z, the static z, by some sampler, right? We can say we can have our encoder encode, instead of encoding z directly, it will try to give me a mu and a sigma, and then I will plug that into some distribution. In this case, we're using the Gaussian distribution, and then we sample a z from that Gaussian distribution, and then we get an x prime. So in this case, for every x, there is an infinite number of realizations for that input x, right? So that's immediately, this is stochastic. Now, how do you force your how do you force your distribution here to actually look something like you impose a prior constraint, like to have the output, essentially the mu and the sigma and all of your data to lie on this normal distribution that we're trying to enforce here. The hacky way of thinking about this, apart from the probabilistic picture, is to think of this way. You have the VAE loss would be the regular reconstruction loss, which is the autoencoder loss, plus some divergence measurement that forces the encoder distribution, which is P of Z given X, to be as close as possible to my prior, right? So I'm just gonna try to add a term to my loss function here. So, and our prior, let's say that we want the P of Z to be a normally distributed 0 and 1, right? And then the output, we want the output of the encoder to match a normal distribution as much as possible. So we plug this in here. We can do the KL divergence. We can use as a divergence here a KL divergence, and then from that you will get just some algebra. You will get this form for mu and sigma. So this is what you would need to add to your loss function. So, and this is what you will see in a VAE loss. There is one more thing that you need to know about for the development of a VE is that you need to eventually do backprop, right? Like you are doing some SGD optimization. So you need to backprop through the network to fine tune the parameters or to find best parameters. And you can't backprop directly through a stochastic layer. So what you do instead is something called the reparameterization trick, which is you essentially replace this, instead of like, sampling and doing this directly, you sample an epsilon from a normal distribution multiplied by sigma and mu. And this is immediately, you can backprop through this. And that's it. This is the VAE. This is the full loss of the VAE. And this is the middle layer. It's stochastic. And there is a prior on the latent space. And that prior I can sample from it and I can decode. Yeah, so what can we do with this? Can we look at the space and actually see if it's meaningful? This is from the original VAE paper. You can see things like if you try to encode this data set of faces into a two-dimensional space, you will see that, for example, one of the dimensions end up being corresponding to frown versus smile. There's a smooth transition there. The other dimension corresponds to a head pose. You can see that you can move the head from one direction to the other. By moving here means that you're walking in the latent space, and then as you're walking in the latent space, and then decode every point along the way, and then you would see that it's actually smoothly moving from one direction to the other. More modern VAE results are very impressive, much more than the original version, of course. You can see these are very realistic photos. Maybe there are some artifacts here and there, but they are very realistic. And actually from that same paper, you can also see examples of interpolation. You can take in your latent space manifold, you can take two data points, this one and this one, for example, and then walk on the latent space manifold. In this case, to be like isotropic Gaussian, right? You're walking in between them, and then you can essentially, you can decode the points that you are seeing in between. Like, look, this is interpolation between two different gender, two different like global features and everything, but still you can get very smooth transition in between them. So we are learning some sort of useful representations of the original data. Okay, so I'll leave VAEs at that. This is just an overview of what VAEs are and what you can achieve, at least the vanilla version of them. And I'll move on to talk about a different latent variable model. In this case, the GANs, generative adversarial networks. So let's again think about it this way. What we want is we want to have some model. This is the latent variables, right? So we want to have some model that takes some z from some prior space and then gives me an x that lies on the data manifold. How do I essentially, if I can say that I can construct this G as a neural network and then try to find the best parameters of this neural network that would map latent space to the real data manifold. But how do I train this G? You can say that, oh, maybe if I have a function that can tell me how close my output X here is to the real data manifold, maybe then I can use SGD and then optimize this network. And then I would get, slowly, this network would learn how to produce, data points that are as close as possible to the real data manifold. Now, the question that people ask themselves is that, can we learn such an F? Can we learn such a loss function? Essentially, this is the output of the generator network. Takes a Z, takes output, and then you have a loss function that measures how far are you from the real data manifold. And the answers of GANs is that yes, we can learn it. So we can essentially say, let me, instead of trying to come up with a function myself, just handcrafted loss function, let me train a neural network to do that. So I'm gonna have a neural network that will tell me, give me some notion of how far I am, how far is the output of the generator is from the real data manifold. But how do I train this loss function? The answer is you train it adversarially. And this is what GANs do, right? Adversarially means that you train the discriminator to differentiate between the fake and the real data, right? Sample from real data, blah, sample from generator, blah, and then you train the discriminator. It has to tell the difference between them. That's why you call it a discriminator or a critic, depending on the setup. And you can train the generator to try to fool the discriminator. So the generator slowly learns how to make an X that is as close as possible to what the discriminator would think is a real sample. And this is essentially the GAN setup. Okay, I could have given time for questions after VAEs, but I'll do that after the GANs. So let's see this in equations. The same thing here that we're talking about, this how to train a GAN. This is the loss. This is the discriminator loss function. The first term here says sample from real data, right? This is X from real data. Pass it through the discriminator, then try to maximize this quantity, which is minimizing the opposite with a negative here, right? So the discriminator tries to give a high score for real data samples. And then the discriminator also tries to give a low score for the fake sample. So sample from the prior, P of Z, pass it through the generator network, take that output, pass it through the discriminator, and then try to train the discriminator to minimize this quantity, which means minimizing the value that the discriminator gives the fake image. You can, and that will slowly build a function that gives you some notion of distance between, random points and or some points and the real data manifold. How do you train the generator? You can just say that, okay, I'm gonna train the generator to minimize the opposite of what the discriminator is doing, right? We're trying to make it fool the discriminator. Yes, that's correct. And this is the minimax formulation, right? One is minimizing the function, the other one is trying to maximize the function. And that's good from a theoretical perspective. However, there's one issue that is related to the fact that we're doing backprop. We're doing backpropagation using SGD, right? And in that case, you need the gradients to be always or mostly large enough. Otherwise, you won't be able to optimize these networks. And the problem with the minimax formulation is that if the discriminator is losing the game, look at this. This is the discriminator evaluation of generated data. If the discriminator is giving the generated data very low values, which means that it's essentially losing the game, right? It's thinking that the fake images are real. Then the gradients will be too small here. This is the blue curve for the minimax function. And that's not useful for SGD. So what we do instead is we just, instead of using this 1 minus d of g, we just remove the 1 minus and then minimize this heuristic loss instead, and we call it the non-saturating heuristic loss. So it has a very large gradients when the discriminator, especially initially, is not confident about the fake data. And this introduces you to the setup of GANs with their original loss. Let me see. Let's see if you have questions, so I know how much time left I have. Okay, let me see here. Okay, I see lots of questions. Okay, would you like to choose 1 or 2 questions?
Sure. Yeah, I can sort of walk you through it. Well, it's on your screen as well right now.
Okay.
Yeah,
let's focus on the questions that are related to the actual lecture material, not the examples that I've shown from climate and fluid, because that's kind of side note.
Yeah, so maybe the second question on, can you use the technique described on slide 14 to separate training and test features with similar distributions? Not quite sure. I know exactly what she's referring to, but
yes. Can we use this technique to separate training and testing data features, similar distributions? I am not sure either what that question means, actually.
okay.
I can try to look at this after the talk. Okay.
Yeah, we can skip that. If there's a more straightforward question. Do you want to take the manifold
Yes,
one?
so the manifold, but why can't we search on a manifold is because we don't have, you essentially, think of this. If I tell you that the underlying function that I sampled the data from is yx is equal to x squared, then you have that formula that describes your manifold, and then you can sample from it as much as you want. But if I tell you that my data is just natural images of celebrity faces, do you have a mathematical description of these natural images or not? And the fact is we don't. We try to construct one, right? And then once we construct one, we can either sample from it or walk on it or do the same thing when it comes to the examples of molecules that I talked about. You have the large space of molecules that could be pharmaceutically useful as a drug. I don't have a mathematical description of that manifold. I need to actually construct some density estimator.
The fourth question by Chris is actually quite interesting. Is it possible to interpolate changes in an image over time using an autoencoder? For example, if you only have hourly images, can you interpolate to make higher frequency data, more temporal resolution using any of these techniques? Sounds like
yes. So it is possible. You would need to. There are multiple ways of trying to do this, but there are temporal super resolution models that essentially do this, right? Like you would learn on certain data, like sequences of time, and then the network, and then you can sample from the points in between those data points. So absolutely, I can refer you to some work on this.
I also hear that the next speaker is going to be telling us about this. So
yeah, okay. Yeah, I think on the question of interpretability, there's a very nice paper and with lots of visualizations and a website called Dissecting GANs. I refer you to that. It's not a yeah, it's still an open question, but that's a very interesting study. Okay, I'll go back to my slides now.
perfect. Thank you.
Sure. Can you see my slides?
Not yet.
Not yet. Okay, I think you need to stop sharing. Okay, now I think you can. Okay, so I have very limited time left, and I think the main part of the talk is already introduced, right? Like the concepts, how do you build these latent variable, the most important latent variable frameworks, and then the rest of it is just results of you know, how people use these frameworks in real life. So first, let me talk about DC GAN, because you will see this in a lot of places. So DC GAN came out in 2015, at the end of 2015. It was the first network that shows how to, or the first work that shows how to essentially build a convolutional based generator in a DC, in a GAN framework. And they have done a lot of hyperparameter sweeps, or somehow they found good parameters and good essentially heuristics that allow them to generate high resolution output images. I think they're the highest resolution they have generated is 64 by 64. This is a modified picture of the architecture from the original one. And DC GAN is essentially, if you want to build a convolutional based GAN, this is the first thing that you would look at. This is the very first example that you would use. And in that paper, you can see all sorts of things that we have seen earlier. You can do interpolation, for example. Again, you can choose two data. Once you train the GAN, you can choose two data points on the prior space, and then decode the points in between them. And then you'll see like smooth transitions from one face to the other. Interestingly, you can even do more than that. You can you have some semantically meaningful directions in the space. So you take a bunch of prior points that generate smiling women, and then subtract, then generate also a bunch of prior, like latent vectors that generate neutral women, subtracted from the smiling women, and then add the vector. This is, we're just doing vector addition in the latent space. We're adding the vector of neutral man, and then you will get a smiling man. Same thing with glasses. So you have man with glasses, subtract man without glasses, and then add women without glasses, you will get women with glasses. And this is pretty remarkable that because this prior space is much lower dimensional, the network is forced to learn some features that are meaningful for the data. There is some sort of organization of the space. It's not just completely random, right? That's also the same result that you would see in the interpolations. It's like it's smooth and dense, and every point, I can't say mathematically, but every point corresponds to something that is close to the kind of data that we have. More modern versions of GANs show extremely impressive results. It's very hard to tell if these images are real or not. This is style GAN 2. This is a modern incarnation of the generator network with ideas from style transfer, and this is what enables the high resolution images that you've just seen. This is style GAN, the original paper, and the other one I showed you is style GAN 2. I won't go through the details of how these style networks work, but this is one of the most state-of-the-art works on GANs. So because these styles, because they learn, instead of directing the Z directly into the network, they learn different, they pass it through a different network. They call it the mapping network that would try to learn styles. And those styles are injected inside the generator network at multiple levels of resolution. So this is 4x4, 8x8, 16x16. Then you learn how to control global versus local features, right? Like coarse versus fine features. And once you train your network, you can see things like this. This is, again, there is nothing in the network that tries to tell it that this is, you need to learn, you know, people smiling versus people gender versus, this is just learned through the training process. So look at this. You have a source image, for example, and then you take parts of the style that generate the source image and you mix it with parts of the style from a different image, and then you can blend the styles between them. So you can blend coarse styles, you can blend the middle styles, and you can also blend very fine styles. So you can see here, this is the image. I'm taking the fine styles from here and just imposing it on this image. The image stays, the person picture of the face of the person looks more or less the same, but it has a lot of the local features, the small features from the source, the style source image. So this GANs are in their original setup, original construction as a generative setup is they're very powerful. But this idea of the adversarial loss, having essentially training a network to learn the difference between two manifolds, is an extremely powerful idea. And that's what we call adversarial training or adversarial loss. For example, it's very useful in domain-to-domain translation. You have images in one domain. You want to translate it to a different domain. Like, see, this is design, this is realization of that design. Pix-to-Pix models have done this, and they use an adversarial loss. The mapping here is one-to-one mapping, but you need paired images to train this Pix-to-Pix. If you don't have paired images, you only have two domains of images, and you want to learn some mapping between them, there's something called cycle GAN, and that's what it does. It learns how to transform between two different domains. The basic idea of cycle GAN is that since I don't have paired images, what I'm going to do is I'm going to have two spaces, and I'm going to perform a cycle consistency loss, which is essentially if I take an image from X and take it to Y and then transform it back using F has to come back as, you know, very close to the original image X, right? And this is cycle consistency. And if you train it this way, you don't have to have paired images. You only have to have two domains. And this gives you a one-to-one mapping. You can do augmented cycle GAN, which gives you many-to-many mappings. This is another work. You can use GANs in super resolution. I think I introduced this earlier today. Essentially, like without the adversarial loss, a lot of the local structures are not reconstructed. Okay, so I want to leave you with a few words about GANs and how you know, how do I actually training them in practice and what are the issues and challenges. They are notoriously difficult to train, but we're learning how to train them better and better. I'll list some of the issues here, try to illustrate some of them, but I won't be exhaustive. First of all, there's no evaluation metric for that capture all the desired data properties, right? So you have the generators generating stuff, and the only thing that is evaluating the generator is the discriminator, right? Which is also learned. But we need more domain-specific metrics to evaluate the performance of the generator, right? And that's not well defined generally. So for vision tasks, people have developed some proxy metrics for human perception, and this is eventually what you need to do. They have to look, you know, visually pleasing to a human, right, or meaningful or consistent to a human. The other issue here is that even the loss of the generator itself is not does not correspond. So when you're training a supervised learning setup, your loss tracks the performance of your network, right? So like it's going down, so you think, yeah, maybe it's going down. I have a validation loss and all of that. That doesn't, we don't have that for GANs, right? So let me show you an example. So you have, this is the original loss that I've introduced earlier today. This is how the loss of the generator looks like. The loss is essentially going all over the place. Maybe it's even increasing, but still the images are getting better. So the quality of the image, the loss curve doesn't correspond to the quality of the image. So you can't use that. You need more domain-specific metrics. People have developed optimal transport-based losses. So the original one is based on a divergence, right? The Jensen-Shannon divergence, but you can use an optimal transport-based loss, and that at least it's argued that it corresponds to image quality. In this case, this is the Wasserstein loss. Yeah, I won't comment more on this. I think in practice, there are mixed results, and people are still using either DC GAN, the original loss, or a Wasserstein loss, or a variation of those, which I'll show here. So there's a zoo of these losses all over the place, and there are some studies that try to see if any of them is better than the other or not. At least the conclusion of the study is that given enough hyperparameter optimization, they all performed. Actually, the original loss performs much better than all of them, but this is given enough hyperparameter optimization, which we don't always have. You can try to, sometimes the discriminator loses the game very early on. The discriminator wins the game very early on when the generator is still like very bad. And then you need to do some tricks like label flipping or something. One of the most common problems in GANs is mode collapse, is that essentially your generator, if your data has multiple modes, your generator only learns how to sample from a single mode. And this is a very common problem in GANs. And it's still an open problem, so there's no like blanket solution that solves everything, but there are heuristics here and there that you can use to, that they might help, they might not help. Eventually, we might actually need to build multimodal priors. So instead of having a prior that is only like an isotropic Gaussian, we need to have a mixture of Gaussian sort of prior or whatever it is. And people have tried things around that area. The other common problem is that the training is highly unstable. So if you train the GAN for a long enough time, you get good pictures, and then if you train it longer, it just becomes bad again. So it's really highly, and it could be much higher frequency. That it's at the level of like steps that it would swing between good and bad results. There are all sorts of tricks for trying to solve this problem. WGAN claim, at least generally is perceived to be more stable than the original loss, but the original loss produces higher quality images. There are some schemes, spectral normalization schemes that are used to try to essentially ameliorate this instability problem. I personally got mixed results on this. I'm not sure if it's the general consensus in the field. And eventually we might need to do something. So a lot of this instability comes from the fact that we're using gradient descent, which is a single player sort of optimization scheme. We're using it for a 2-player game. So you might want to include the information, like when your discriminator is taking a step, it knows also that the generator is going to take a step using gradient descent. So it can incorporate that information in its own loss function, right? In its own step. And then the same way that the generator incorporates that. And you can do that at infinitum, right? You can say, I know that he knows that I know that I'm going to move in that direction. And then you can include all of those terms, right? So there is, Florian and Anima have built something, developed an optimizer for this problem, which for a two-player game. And it's called the CGD, Competitive Gradient Descent. It's promising, but I think at least at this current stage, it's still computationally expensive. But this might be the direction where we go with GANs. There are lots of other open questions. I touched upon some of them. This is an excellent article by Augustus Odena on distill.pub. If you don't know distill.pub, you'll be pleased to see all the pedagogical articles there. But this particular article is very, very interesting. There's one type of generative model, a class of generative models that I didn't touch upon today. It's also a latent variable generative model, which instead of in the VAE, we try to, as I said, we try to build an approximate. Essentially, we have a lower bound on the likelihood of the data P of X, right? There is the flow models. They build essentially using some invertible transformations. If you have an invertible transformation going from X to Z and then from Z to X, they show that you can, instead of doing a log P of X, which is intractable, you can't sample all the X space, you can transform that all the way to the Z space, and then do a log P of Z, right? And log P of Z is tractable because you have a, if it's a Gaussian, isotropic Gaussian, for example, you can just impose do a maximum log likelihood on that, right? And sample as much as you can. And this is the main idea behind normalized flow models. Is that using invertible transformations, you can do an explicit maximum log likelihood optimization over the P of X. And there are results that are not as, there are high dimensional results. They're not as yet as good as things GANs and VAEs, but they're getting there. In the article that I mentioned, it discusses a little bit the trade-offs between these different generative models. There are resources that I post here, especially the practical tutorials resources that you can take a look at here. I especially like the Jan Lucans and Joshua Benjo's, these talks by them. And there's a 45-hour, I think, deep unsupervised learning class at UC Berkeley with all the videos online if you want to get more into the details. Thank you.
Thank you, Mustafa. And maybe we can pull up the Slido questions once again to check out any new questions.
Okay. Yes, so in climate science, so I won't speak directly about GANs, but yeah, generally generative models are used for debiasing. There are a lot of results, at least using VAEs, that do debiasing for data using a VAE. I think that's maybe a place where you want to look. I don't know much about using GANs for that, but maybe somebody has tried. I don't know any climate related GAN tutorials.
Yeah, it's a pretty new topic, and there isn't actually a whole lot of work in GANs for climate science. I think we're just starting to see a few studies coming out. So you might need to wait for a year or two, but that said, this is a good time for you to dive into applying GANs for climate.
Yeah, I can plug my, I have a GANs for stochastic parameterization paper that appeared in the James, the Journal of Advances in Modeling, or I forget the whole acronym, but if you look on my Google Scholar page, there's a link to it, and it has a little bit of explanatory information on GANs as well.
Okay. So how easy is it? I think I answered this interpretability questions. Can we use generative model to do improved satellite or data or data simulation? I think this is an active area of research and people are thinking about this exact question. So I think the answer will be yes. Can you use, concrete examples for how GANs. I mean, like, think of GANs not necessarily only as a generative model, but think of the idea of this adversarial loss, which is really, really helpful in so many applications, right? So you can think of, for example, maybe you can use super resolution with an adversarial loss to do to change the resolution of data from one resolution to the other, right? Maybe we can use the whole idea of generative models to create a reduced order model, right, of some system. Maybe we can use an adversarial loss to do in a setup where I'm trying to do spatial temporal modeling for climate systems. Yes, maybe you don't need necessarily the consistency of every single frame to be accurate, but you need the global statistics over 10 years or 100 years to resemble the model that you have. Instead of using your simulator that is very expensive, very computationally expensive, you can try to fit a GAN to the simulator and then run that much faster. So there are a lot of ideas here. I think I'm not an expert in climate or in fluid dynamics or any of that. I think, but I think people on this board will probably be able to answer this question better. But yeah, from what I mentioned, there are lots of work on these fronts.
We're almost out of time, but I'd like to ask you one question that actually has come up in a few different talks so far through the week. If you were to train a GAN or any other unsupervised model on the current present day climate, a data distribution from today's climate, are there ways to make it be able to generate data of future climates?
That's a good question. I think I can tell you my hunch. What I gather, my understanding right now is that the climate system is semi-stationary, right? So it's not like a completely stationary distribution, but it also doesn't move erratically, which means that maybe with some data assimilation technique or like some model calibration, we will be able to make the GAN essentially adjust its output for much longer periods of time. This is a forefront area of research, so I can't give a concrete answer, but this is where what I think will happen.
Thank you. I also see that Claire is going to tell us more about this in the next talk later today. So, well, let's thank Mustafa again, and thank you for taking the time and joining us today to enlighten us on deep generative models. We will take a short break now for about 8 minutes and then resume with the next speaker at 10 minutes past the hour. Thank you very much.
Thank you. Thanks for the organizers too. Bye.